So hello everyone, good morning and welcome to Discovery, which is our second workshop set for Astro Sprint. And we are starting off today with a talk by Fei Dai on TESS. Fei will be talking today morning as well as tomorrow morning. So do attend and welcome Fei. Thanks for joining us.
Thank you, Priya. Should I get started?
Yeah, please do.
So thank you, Priya, for the kind introduction and the invitation. It is my great pleasure to talk to a group of aspiring scientists like you. I am currently a postdoc at Caltech, and I work on exoplanets. So my talk today is about the Transiting Exoplanet Survey Satellite Mission, which is also short named TESS. So TESS is a space mission built by both NASA and the MIT. And it has been the workhorse in discovering more than thousands of transiting exoplanets since its launch in 2018. So along with many of my colleagues in exoplanets, we actually work with the data provided by TESS on a daily basis. So before we talk about TESS, let us briefly review the status of the exoplanet field, since this might be new for many of you. So the first exoplanet, 51 Peg B, was discovered in 1995. Since then, exoplanet search has been the fastest growing field in astronomy. Up to now, there are about 4,000 exoplanets discovered by a variety of different methods. So this is a diagram showing the known exoplanets in orbital periods versus planet mass. You can see that the various discovery methods tend to discover planet in different regimes in this period versus mass parameter space. And today, we will focus on the transit and the radial velocity method, which are by far the most prolific detection methods responsible for discovering more than, I think, 80% of the known exoplanets. So how do these two methods work? So this video, let me see if it runs. Yeah. So this video shows the transit method. If you monitor thousands of stars, chances are some of them will host an exoplanet. Moreover, the star and the exoplanet may be aligned with the observer's line of sight. If that's the case, the planet will periodically transit the host star. So when the planet transits, it blocks part of the host star from the observer's view. So the observed brightness of the host star will drop a bit. So by modeling this brightness change over time, we can infer the presence of a planet as well as its radius and orbital period. The other method, radial velocity method, is also shown here. Because of the gravitational pull from the host star, a planet will revolve around its host periodically, and the orbit is well described by the Keplerian solution. And from Newton's second law, we know every action has a reaction. So the star is also performing Keplerian motion, although on a much smaller orbit. So one measurement we can make is to monitor the stellar spectrum over time. Due to the Doppler effect, when the star is moving towards us, its spectrum will be blue shifted to shorter wavelengths. When it's moving away from us, it will be red shifted to longer wavelengths. Again, this periodical change of spectrum or radial velocity can alert us to the presence of a planet. And the amplitude of this motion actually encodes the mass of the planet. Sorry, I forgot to play the video. As you can see, the radial velocity, which is shown on the right, changes as a function of time periodically. And the observable is this shift of the stellar spectrum shown on the bottom right. All right, now we know how the two most prolific planet discovery method works conceptually. Let us examine how they work in practice. Before we talk about the TESS mission, let's first look at the Kepler mission to set the stage. In many ways, the Kepler mission was TESS mission's predecessor, and the Kepler mission was extremely successful. The vast majority of the confirmed exoplanets were actually discovered by Kepler. actually more than 2,600 of them, reported in nearly 3,000 papers. Kepler was launched back in 2009 and lasted for more than a decade. And it observed about 500,000 stars during that time. So how does Kepler actually discover planet? So the plot on the left shows a field of view of the Kepler mission. The Kepler mission actually looks at a very small patch of sky near the constellation Cygnus. The grid pattern you can see on the left plot actually reflects the layout of the CCD detector on the telescope, which is shown in the middle. The CCD detector, or the charge coupled device, are basically semiconductors that give off electron when a photon hits a pixel. So by counting the number of electrons generated in each pixel, we can infer the amount of light incident on that pixel. And on the right is an actual image of the night sky from one of the CCD detector. As you can see, there are thousands of bright stars visible in this image. When we focus on the vicinity of one star, which is shown in the middle, which is a zoom image of the CCD detector. So we can see that light from one star will be spread out into many neighboring pixels. So we can draw out like a bounding region, which is shown in the red, and we sum up all the photons or electrons in those pixels to represent the brightness of the star. So we can do this summing exercise periodically to monitor the star's brightness over time. This is something we call the light curve, and we will use that later. So the plot on the right shows the measured light curve from Kepler, corresponding to the planet Kepler 7b. So after 9 years, or even 10 years of observation, Kepler has made some really exciting discoveries. So here we'll just highlight a few of them. The first really important discovery is that if you compare the number of stars being monitored by Kepler with the number of planets you discover, you can actually calculate the occurrence rate of exoplanets. It turns out that nearly every sun-like star in our Milky Way galaxy holds about one planet. So the plot on the left shows the relative occurrence rate for planets of different sizes. For example, the leftmost histogram shows the occurrence rate of Earth-like planets. The second histogram shows the so-called super-Earth, that have radii between 1.25 to about 2 times that of Earth. The third histogram shows a mini Neptune between 2 and 4 Earth radius. And you can also see the larger icy giants and the gas giants on the right, which are rarer. So perhaps one of the strange things is that the most commonly occurring planet in our galaxy are the super-Earths or the mini Neptunes, which typically have orbital periods of about 10 days. However, we do not see such planet in our solar system. On the right is another important discovery in our recent years about the Kepler mission. So just now I mentioned that there's this distinction between super-Earths and mini Neptunes. So the curious of you may ask, where do you draw the distinction? Why do you put 2 Earth radius as a boundary? So the plot on the right actually explains this distinction. If you look at the occurrence rate of planets spread out into different planet sizes, you can clearly see a gap at around 2 Earth radius. So this gap has been attributed to the different composition of small planets, with the smaller peak composed of Earth-like rocky planets, and the larger peak actually composed of planets that still host a tenuous atmosphere. Therefore, its radius is much bigger. So this distinction between super-Earth and mini Neptune is actually based on this observed radius gap. Kepler's main mission was actually to quantify the occurrence rates of Earth-like planets around sun-like stars, the so-called habitable planets. To achieve that goal, Kepler mostly stared at a very small patch of sky for several years. The hope was to catch a few transits of those Earth-like planets on yearly orbits. To be more precise, the habitable zone can be defined as a radial distance from the host star, where the temperature is suitable for maintaining a water-based ocean on the planet. And life as we know it depends on water, which is a universal solvent. So looking for water ocean is a natural prerequisite for searching for life on exoplanets. So if you actually look at the habitable zone across different stellar types, which is shown here in this plot, as the stellar mass goes down on the y-axis, the star will give off less energy per unit time, or what we call luminosity. So as the stellar mass goes down, its luminosity goes down, and the habitable zone actually moves closer towards the host star. For sun-like star, the habitable zone is about 1 AU, where our Earth resides. But for a really low mass M dwarf, the habitable zone can be less than 0.1 AU. So one thing I forgot to mention is that for transit search, shorter period planets are much easier to detect compared to longer period planets, given that they transit very frequently, and you can stack the different transit to achieve a higher signal to noise for detection. All right, with that short introduction, I think we are ready to move on to TESS mission. So in many ways, TESS will help us answer the open questions left by Kepler by adopting a very different survey strategy. I'm gonna take a pause here and let's view this video together made by, I think, the MIT team about TESS.
TESS, Transiting Exoplanet Survey Satellite, discovering new Earths and super-Earths in the solar neighborhood. TESS has a simple stair and step observation strategy. TESS points anti-solar and remains fixed in inertial space for 27 days, or 2 orbits. TESS is a 2-year all-sky survey mission with 26 observation sectors, or 13 sectors per year. The overlap of the observation sectors near the pole is optimized for JWST's continuous viewing zone. After completing the northern hemisphere in year 1, TESS transitions to map the southern hemisphere in year 2. 13.7 days, TESS orients to point the Ka-band high-gain antenna towards one of 3 DSN stations for science data downlink. After the nominal 3-hour downlink is complete, TESS reorients back to science mode. Following the launch from Cape Canaveral Air Force Station, TESS is placed into a 600-kilometer parking orbit. The lower adapter structure is released from the solid rocket motor. The satellite and the SRM stack spin rate is increased to 60 RPM. The solid rocket motor ignites, sending TESS into its first phasing orbit with a nominal apogee of 250,000 kilometers. The solid rocket motor burns out, and the sped rocket motor is released and falls away. TESS despins using onboard thrusters. TESS deploys its solar panels. TESS has only one deployment. At facing orbit perigee, TESS performs a burn to increase apogee. TESS uses lunar gravity assist for mission orbit insertion. Following the lunar flyby, TESS transport orbit has a nominal lunar inclination of 37 degrees en route to Pleiades. At PLEP, TESS performs the period adjust maneuver to reduce the mission orbital period to be 13.7 days, a 2-to-1 resonance with the orbit of the Moon. Lunar perturbations are roughly averaged to 0, with the Moon leading or lagging TESS at apogee by 90 degrees. The HEO orbit is stable over decades. TESS will discover new Earths and super Earths in the solar neighborhood.
All right, bring on the slides. Okay, so that was a quick review about the TESS spacecraft. Let me just say a few things about the technical details. So I think TESS will observe something like 200,000 nearby stars with 2 minutes observational interval. And you will observe millions of stars with 30 minutes interval. And the spacecraft has 4 lenses, each has about 10 centimeter diameter. And the lens or the detector will actually cover the wavelength range between 600 to 1,000 nanometers, which is suitable for discovering more planets around lower mass stars to assess their habitability, as we mentioned earlier. And to recap from the video, we know that TESS is in the so-called high Earth orbit, which is roughly 1 to 2 resonance with the lunar orbit, since this orbit will avoid obstruction from Earth and the Moon maximally. So this slide actually shows the field of view from the TESS CCD, which is much larger compared to Kepler. And you can see that each of the 4 cameras will cover roughly the size of the constellation Orion. Another key point I mentioned earlier was that Kepler told us closing planets, super Earths or mini Neptunes, with orbital periods about 10 days are extremely common in our galaxy. So TESS only needs to observe one patch of the sky for about 1 month before moving on to the next patch. And 1 month is usually enough to detect many of the closing exoplanets. And most of the night sky will have about 1 month of TESS data. However, the ecliptic pole will have more or less continuous coverage up to a year or so. So this so-called continuous viewing zone will provide us the chance to discover long period planets, and it will also happen to be the area where the upcoming James Webb telescope will be able to observe these planets for follow-up studies. So the Kepler's point and stare strategy missed out on a lot of the nearby bright stars that are amenable to more detailed characterization. TESS, to complement Kepler's result, actually adopted the nearly full sky strategy, which is a short duration but larger spatial coverage. This will help us to review the closest, brightest planet host. So in this figure, we can see that the Kepler field of view, which is in the upper right, only covers about 0.5% of the night sky, whereas for the TESS mission, its field of view will be almost 85% of the night sky. Given the upcoming extended mission, I think TESS will almost cover the entire night sky. All right, the best way to visualize the planet sample provided by TESS is to do a comparison study with the Kepler mission. This is perhaps best shown in this short video. So in this video, we are seeing the distance between Earth and the various planet hosts across the night sky projected into 2-dimensional space. The orange points are planet hosts discovered by TESS, while the blue points are those discovered by Kepler. And you can see that TESS all-sky strategy allows us to discover many of the closing planet hosts across the entire sky, whereas the stare and point strategy by Kepler discover a narrow cone but very deep phase space of planet hosts, which extend to several thousands of light years. All right, going back to the presentation. So this plot summarizes the video by plotting the planet radii versus their distance from Earth. and the symbol size represent how suitable these planets are for follow-up characterization. The key thing to know is that a nearby star will be much brighter than a more distant star. So its planets will be much more suitable for detailed characterization, as most of these characterization will be starved from photons from the host systems. So the brighter they are, the easier we can study them. So to just name one of the follow study, we actually want to measure 50 precise mass radius for the TESS planet. This is considered the key objective of TESS mission. So these mass radius measurement will allow us to study the compositional diversity of exoplanets. So the question one may ask is are the exoplanets mostly Earth-like planets with an iron core on top of which you have a silicate mantle? Or are the exoplanets more like Mercury, especially the closing ones, which are expected to undergo a lot of giant impact collisions? In which case, one may expect a higher iron fraction for these planets. Another question we can ask is, are the exoplanets' composition also linked to the composition of their host star? Also, are some of the lower density planets we see actually made of volatile materials such as water in their mantle? So all of these questions can be answered to some extent if we get enough planets on the so-called mass radius diagrams and compare the distribution of the observed planet with theoretical mass radius curves for various compositions. One final point I want to mention is that for the upcoming James Webb telescope, we will study many of the planets discovered by TESS. For example, TOI 421b is the subject of an accepted JWST program, which is shown on the bottom. So the observation these authors propose is that when the planet transits the host star, we can measure how the planet atmosphere further puts its imprint on the host star spectrum. So for example, some of the more prominent species in the atmosphere, such as sodium and potassium, will leave strong absorption lines in the stellar spectrum. And by modeling these absorption features, we can deduce the composition as well as the thermal pressure structure of the atmosphere on those exoplanets. Okay, I think that was my final slides. So today we have done a brief introduction into the TESS mission and how transit and radial velocity method works. So tomorrow, what I had in mind is that we go through this paper reporting the first discovery, the discovery of the first exoplanet from the TESS mission led by Chelsea Huang from MIT. So if you have time, please take a look at this paper before the meeting. So the second part of the meeting for tomorrow, we will actually play with real TESS data and do some planet discovery ourselves. So I'll probably send a Python notebook to Priya, so the participants will have a chance to look at those before the meeting. All right, that was my presentation today. Let's maybe move on to questions.
Yeah, so Fei, you have half an hour more, but we can start with the questions, and then if you want, you can still talk for some more time because we do have some more time allotted to you.
Sure, yeah.
So there's the first question by Anoop was why was resonance with the lunar orbit necessary for the TESS orbit?
So I'm not an expert on orbital dynamics. I think the orbit was designed by JPL, and I think one of the reasons is to avoid obstruction from Earth and Moon. So if you're in a resonance, you can always avoid the lunar orbit at appropriate times and shift your pointing accordingly. The other reason, I guess, would be stability of the orbit. So resonance If you put an orbit in resonance in the correct phase space, it can actually help maintain the stability of the orbit. So you don't need to use as much fuels to maintain the orbit.
Thanks. So the other one, how do you know whether, okay, so with this thing, how do you know whether the planet is Earth-like other than being on the habitable zone? Other than habitable zone, what are the other methods?
Right. So the first thing we can do is by modeling the transit light curve, we can figure out the planet radius compared to the stellar radius. This is basically the depth of the transit. So you further characterize the whole star by measuring its spectrum. We can figure out how big the star is. So we can translate the transit depth and the whole star radius into a planet radius. So it depends on how you define Earth-like planet, but usually people take Earth-like planet to be those within maybe 0.8 to 1.2 Earth radius. It's up to you to draw the boundary, but the first thing is, of course, the radius has been rather close. The next thing you can do is measure the planet mass by radial velocity. This is basically the amplitude of the star's reflex motion caused by the planet. So a larger planet will cause a larger reflex motion. And this is done by the Doppler method, as I mentioned. So if the planet both has Earth-like radius and Earth-like mass, then it's very likely it is probably also rocky like Earth. And the next step we want to do is to actually characterize the planet's atmosphere by doing, say, transmission spectroscopy on the planet when it turns to the whole star. For really Earth-like planets on yearly orbit, this observation is really challenging. I don't think the upcoming JWST will be able to do it even. So the community's solution is actually to look for planets around lower mass stars, so-called the M dwarfs. For M dwarfs, since the star is smaller, the transit signal is much bigger, and the star's reflex motion is also larger. And the planet's orbit within the habitable zone is also closer to the host star. So it's a triple plus plus for the M dwarfs for detecting planets that can be potentially habitable. So those will be the priority for the JWST spacecraft.
Yeah, thanks. So there's a related question on how do we calculate? How would you actually calculate the distance to the Goldilocks zone for different stars, as it will vary according to characteristics of stars?
Yeah, sounds good. So to define the habitable zone, the first and very simple calculation we do is the amount of stellar insolation on the planet has to be such that its surface temperature is close to, well, it's within the range of water is liquid under normal atmospheric pressure. So this is usually taken as 0 to 100 degrees Celsius, or if you convert it to absolute Kelvin scale. So the first definition is very simple. You just take the star's luminosity, calculate its energy output at various distance, and you can lock down a radial extent where the energy is just correct, so that the planet orbiting the host star in that region will have its surface temperature within that range. So this is level 1. Level 0, definition of habitable zone, and you correctly identify that different stars will have different characteristics. For example, M dwarfs, although they are favorable for discovering habitable planets, as I mentioned earlier, one drawback they have is that M dwarfs are fully convective. So dynamo effects are very effective on M dwarfs. As a result, M dwarfs are known to be more magnetically active than sun-like stars, giving off a lot of so-called flares of stellar wind. And this can be detrimental to the habitability of the planet. And you can potentially take this into account when you define the Goldilocks zone. but that requires a detailed understanding of M dwarfs, which is still being studied. And another complication is that the composition on the planet also changes the Goldilocks zone. For example, we know global warming is a problem and caused by greenhouse gas on Earth. The same thing can happen for exoplanets. Its composition of the atmosphere will actually determine how much light gets absorbed by the surface versus how much light is reflected into space, and that will change the region where water-based ocean can be hosted on the planet. So if you want to answer this question in detail, there are a lot of things you have to consider.
And then there's a question by Tejinder Pal Singh, which I can answer. Is there a project related to TESS? Well, there is a project which Fei will talk about tomorrow. So like he mentioned, I'll share the Jupyter notebook with you today, so that then you can work, you can, parallelly work in a hands-on session tomorrow morning. So tomorrow, yes, there'll be the project. There's another question by Debashish. Do any set of exoplanets around any star follow the Titius-Bode law?
Okay, sounds good. So let me give an introduction to the Titius-Bode law. If I remember correctly, I think I learned this in high school. So the Titius-Bode law states that if you plot the orbital period or the orbital distance of the solar system planets, and you fit, I think it was a quadratic polynomial to it, then the planets follow that polynomial very closely. I forgot whether it's a polynomial or some other function form. Either way, it's not a physics-based law. It's more like a mathematic coincidence. And the solar system planet follow very close to that mathematical form. So many people have tried this for exoplanets, fitting a similar set of laws to exoplanets. Some found some success, some didn't. So one thing I should note is that for most of the exoplanets we know, we do not detect the entire planetary system. Usually the planets, we only detect the closest or the closest few planets from transit radial velocity. This is because both methods are much favored towards short period planets. And then, as I mentioned, from Kepler, most of the planet discoveries are for planets within 1 AU. Actually, most of them have orbital periods of 10 days, but we don't have such planets in the solar system. Mercury, being the shortest planet in the solar system, had 88-day orbit, but many of the exoplanets have much shorter orbits. So the bottom line is that we do not know the entire inventory of planets for many exoplanetary systems. Usually the number of planets is only 1 or 2 or 3. So you can hardly fit a Titius-Bode law. I think the number of parameters in Titius-Bode law is 2 or 3. So you at least need 3 planets to constrain that problem. Anyway, personally, I don't think Titius-Bode law is significant. I think it's more like a medical coincidence, but I might be wrong. And I don't think there's a consensus on this in the community, whether the Titius-Bode law carries any physical significance.
Yeah, I'd agree with Fei. It's a neat idea at that time, but obviously, since there's no physical connect, right? So
Yeah.
So now there's another question by Sakshi. You just said that M dwarfs have a strong magnetic field. How do we determine that?
Let's see. Okay, I'm not an expert on M dwarf magnetic fields. So what you hear from me is secondhand. I think there are a few things. First of all, M dwarfs flare. You can detect those in the light curves. So flare, if you look at the sun, flare is something like a sudden burst of energy on the stellar surface or the chromosphere. And the burst of energy will release a strong wind out of the planet, as well as a corresponding increase in the amount of light the star outputs. So if you monitor the stars over time, sometimes you're lucky you can detect a stellar flare. And you count the amount or the rates of stellar flares on various stars. And it turns out that M dwarfs flares more often than sun-like stars. And the proportional energy contained in one flare is greater compared to sun-like stars. And back to one thing I forgot to mention that is that stellar flare are closely associated with magnetic field. I think the physics is so-called magnetic flux tubes. So we know in the sun, magnetic field is generated in the so-called tachocline, which is the transition region between the radiative layer and the convective layer. So in the transition region, the tachocline, there's a lot of velocity shear, meaning that the lower layer moves at a different velocity from the upper layer. So if you have a strong velocity shear, and you look at the Maxwell equation, that velocity shear will actually generates a lot of magnetic field. So in the sun, at least we know that in the sun, the magnetic flux tubes get generated in the tachocline. And when you have magnetic fields itself will generate so-called magnetic pressure, which will help to balance the gravity along with thermal pressure. So you have a region of stronger magnetic field. Its thermal pressure can be lower, meaning that the density in the tube will be lower. So the flux tube will tend to rise, so-called magnetic buoyancy. So when the tube rises to the stellar surface, you will produce two footprints on the whole star. And those footprints are the star spots we see. So when the tube reaches the stellar surface, it can be maintained for a while, but eventually it may get unstable and the tube will destruct itself from magnetic reconnection. And that destruction will release all the plasma contained in the tube into interstellar space and cause flares. I think that's the basic picture. So the flares are related to the strength of magnetic field on the whole star. And for M dwarfs, we see stronger, proportionally speaking, and more frequent flares. I think that's the main reason why we think M dwarfs are more magnetic than active.
Thanks, Fei. There's another question which is a little long by Anup. If stellar conditions like convection and local planet conditions like greenhouse effect affect the habitable nature of planets, could we be missing planets that are potentially habitable despite being outside the habitable zone as per the definition? So how many planets could we be missing or miscategorizing due to insufficient data because of low signal in larger stars?
Very good question. So my personal philosophy is that we have to start answering the question, any physical question, in a simple way, as simple as possible, just to get things started, just to build a ground point before we add more details. So if we take the traditional definition of habitable zone, there are about a dozen planet candidates discovered so far in the habitable zone. And if you're willing to add in more physics or more possibility, then the habitable zone will surely increase. But this thin line between adding more physics to risking like losing your argument at all. So I don't think the community has reached a consensus on how far we should extend the habitable zone. And you're right, there are definitely planets that we could be missing. But to answer the question at the ground level or at the first step, the community agreed that we should probably just use a simple definition.
Yeah, thanks. There's another one which is slightly overlapping, but I'll still take it. Rajlala Sharma, how can we find signs of life in exoplanets?
Okay, this will be, I don't know, I'll try to refrain from long-winded answer. So this same question has been asked on Earth by none other than Carl Sagan. So I think this was back in the 70s. Carl Sagan asked the science community, okay, let me challenge you. Can any one of you determine that Earth pretend that we don't know life exists on Earth. Can you tell from, I think it was one of the spacecraft we sent out to Jupiter, I think it was Voyager or one of them, using this instrument on that spacecraft, we point back at Earth, and by that point, Earth looks like just a pale blue dot.
Yeah,
on the
that's
detector.
Voyager.
Voyager, okay. And using the data from Voyager, can we tell that life exists on Earth? I think the answer was, first of all, the so-called vegetation edge is that plants on Earth perform photosynthesis, and the chlorophyll has a particular characteristic, is that it absorbs light in the optical, but reflects a lot of light in the infrared. I think this is to help the plants from overheating. So this strong reflection in the infrared is called the vegetation edge. And it's not associated with any process other than life. No geological or chemical process can explain that. I think that was one of the key points why we know life exists on Earth, if we just look at Earth from distance. So for exoplanets, one may attempt the same. The other way we can do it is to look at water or other so-called biomarkers. So if you look at the exoplanet in transmission, as I mentioned in the last slides, the stellar light coming through the planet will be scattered or absorbed by the molecules in the atmosphere. So depending on how puffy the planet atmosphere is, or the composition on the atmosphere, so you will see a different pattern of absorption for that planet. And by modeling that pattern, you can figure out which species or which molecules are present in the atmosphere. And the first thing you can look for is the water in the exoplanet. But water is a very commonly occurring species. You only need hydrogen and oxygen, and it's pretty well produced given the correct conditions. So many people say water will not be definitive. So the next thing we ask, okay, what would be the definitive molecule that's only produced by life? Some say methane, which is harder to produce geologically. Some say a variety of other molecules. Actually, there are few of my colleagues that actually dedicate their career on this, on figuring out which molecules should we look for in the near future to indicate life. But at this point, I don't think there's a consensus on which molecules are definitively associated with life, or life as we know it. If we consider other forms of life other than carbon-based, water-basing life, then the answer could be much wilder, and nobody knows the answer.
Thanks, Fei. Yeah, the problem is there are many questions to be answered, and that's what we need everyone for.
Yeah, thanks, Fei.
So I think that we had a really good set of questions. Which question?
It is, how does the size of a planet matter in determining if it's habitable or not?
Very good question. Very good question. So the reason we are looking for Earth-sized planets is that, well, as we have seen, Earth has the capability of, well, a few important things are happening for Earth so that life can arise. First of all, it's in the right orbital distance that liquid water can exist. And liquid water is a universal solvent, and many life chemical process happen in water. The other thing is Earth is big enough so that it doesn't cool fast enough. So its interior is still molten. This molten interior is important for generating magnetic field, and the magnetic field will help Earth maintain its atmosphere. If you look at Mars, Mars is much smaller than Earth, so it actually cools much faster than Earth because of the higher surface area to volume ratio. So it is believed that Mars interior is no longer molten, so it can only maintain a very weak global magnetic field, or some say it's not even global. The moon is important. It helps the Earth slow down. It doesn't spin as fast, and it produces tides on Earth. And the importance of tides is that for life to evolve, you need some sort of stress, and the tides produce a daily stress. If you look at the puddles near the shore, those puddles will periodically get evaporated and refilled with tides. So those puddles will have a lot of stress, and life in those puddles are forced to compete with each other for a limited amount of resources. And the first lives actually evolved rapidly in those puddles. So I have said a few things about Earth. Well, another thing I should probably mention is plate tectonics. This actually helps the Earth recycle a lot of things and produce various different molecules in the atmosphere. Anyway, the reason why I mentioned so many fortunate things about Earth is that for detecting life, at least in the near future, we're looking at Earth-sized planets for starters. The reason why we don't look at super Earth or mini Neptunes, which are very common in our galaxy, is that for super Earth, the gravity is very strong, and that can have some detrimental effect. For example, super Earths of mini Neptunes, their gravity is strong. They can actually hold on to a lot of atmosphere, including hydrogen and helium. And in those atmospheres, life may not be able to breathe, or the surface pressure is much higher. So another point is that not enough light will reach the surface of the planet, and we need light to drive a lot of chemical process or energy gradient for life to evolve. So Earth-sized planets is our first take on this question.
Yeah, thanks. Do we have any more questions? Actually, sorry, I could have mentioned that earlier. Participants can unmute themselves also and ask if they want. I'm sorry.
Yeah.
I should have.
Yeah, no question is a dumb question. If you have any question, just go ahead.
Yeah. And so I think this breakup worked out well, that you spoke for half an hour and we've had almost 25 minutes of questions. So that makes it good.
It'll be hard to get people's attention for the entire hour. I myself get tired after listening.
That's right. That's right.
Hour.
That's right. So, Fei, let's talk about tomorrow. So you'll be giving me the Jupyter notebook, and everybody should have their systems, laptops on, and they can work parallelly, right? For tomorrow's session?
Yeah. So I think the best way is that we go through it together. Mm-hmm. And after the session, if people are interested, they can use the same set of code on exoplanets and try their luck at discovering the planet in there. Something like that.
Yeah, I mean, the plan is that everybody would be doing projects. In this one, everybody is supposed to be doing projects, which then they can present next time. So this is AstroSprint is made up of 3 workshops, and in the workshops we have the material, and then in the period between workshops, students can work on what they did and they be present. So even in this workshop, there'd be some students presenting on what they started on last time. So today also we have sessions on that later on. So the idea is to make to do projects. That's the basic idea. So what you'd be giving is the feeding material, and then
the projects are the best way to learn.
That's true.
Yeah, these sessions are to basically incite their interest and also to tell them what are the open questions and what can be done and how can they tackle. And then we hope that people who are interested can come back to you if they have doubts and issues, and you can in some way mentor them so that they can work into a proper project.
All right.
I hope you'll have time for that.
Well, let's see. I probably wouldn't have time to supervise 40 students, but if it's short questions, I can definitely help answer.
Okay. Yeah. Fine. That's fine.
Yeah.
So, so if there are no more questions, I'll just wait for a half a minute for questions, and then we can wind up the session.
Sounds good.
Yeah. Okay, I don't see any more questions. Okay, sorry, Fei, you could go on.
It was just asking, it may not be questions related to exoplanet or astronomy. You can ask me a question about what science is like.
Oh yeah, great.
Or
Actually,
like
yeah, Faye and me were together on another program, and I think in that, the mentor profiles was something a really, interesting thing for students to know how you actually got into the field of astronomy. So even I can ask you that question now, if you can just briefly tell us how you got into astronomy and what was your experience till now as a postdoc.
Sure. Yeah, you can briefly say a few things about that. So I don't think I was very interested in astronomy when I was a child. I think I only got very interested in it in high school. I joined my school's astronomy club and made my first encounter with stars, galaxies, nebulae with a small telescope. I think it was a 8-inch Schmidt Cassegrain. So we made a lot of observation of the celestial objects, and that really got me interested. So I did my undergrad in the UK doing physics, knowing that I will probably go into astrophysics in my later years. And that's what I did. I think I fully switched to astrophysics in my final year. And I did a project, I think, accretion disk simulations. And I think shopping for ideas or shopping for areas where I can work as a graduate student. And Exoplanet really suited my interest in both astronomy and geology, and some bit of biology too. So it's a really interdisciplinary field. So I went to MIT and asked a few people working at Exoplanet if they are willing to take on students. And I found my advisor, Josh Wynn, was taking students. So we started working. Usually people do a few rotations during their grad school, like maybe they try out galaxy simulations, cosmology. But I like the exoplanet a lot, so I just continue working on it for 5 years as a graduate student, and now for 2 more years as a postdoc. Still have a lot of passion for the field, and with so many missions coming up, there are a lot of exciting science to be done. So if you're looking for fields, for your graduate career in astronomy or in particular exoplanetary science, can be a very important one on your list. Just check it out. Yeah, it might be your passion.
Yeah. No, the purpose of the course is basically because in India, for example, there are very few astronomy courses at undergrad level. Even at postgrad level, it's only at few select places. So
Right.
that's why, we had this course so that people can actually do things, because otherwise it's not part of the curriculum. As part of the curriculum, there's just very little bit of astronomy, a little bit of mention of it, but nobody goes deep. And there's plenty of material at outreach level. But the problem is if you want to work, that's difficult to find. Either it's a bit too specialized that you can't understand, or it is too outreachy.
Yeah, I totally relate.
And to add to what Priya said, we have a lot of very intelligent and good students who have been pushed into engineering or areas, but their heart lies in astronomy or so.
Right.
So it's to get them together, use their skills, and see that they can build a career in what they actually have a passion for. So there's a lot of interest in astronomy, but there are no specific courses for them, except for in 1 or 2 universities.
I see.
Yeah.
Yeah, I'm really happy to be part of this program and
Yeah.
give you my perspective on this. As Priya mentioned, we were actually part of an earlier workshop that teaches coding and basic research skills. I don't know if Priya shared our GitHub repo with you. There's some very good information in there to get
Yes,
started.
I'll share that. I'll share that. The videos are also there. Yeah, I'll share it with the part. So thanks a lot, Faye, and
Sure.
see you tomorrow.
Yeah.
And everybody ready with your laptops and the Jupyter notebooks. Yeah, you can use Google. They can use Google Colab also, right? If they don't, if they've not installed Python,
Mm-hmm.
Google Colab will be fine also. Okay, thanks a lot. So see you,
Sure.
Faye.